Hey chemists, we're going to start the unit on stoichiometry today. That essentially means talking about quantities in chemistry. Chemists are interested in making things, and we want to have a way of describing what quantities of things we can make. That's one reason we do this. So we're going to talk about two things today, specifically all those numbers that we see on the periodic table, the atomic masses and their relationship to isotopes, and then how we convert and use things like molar mass and mole conversions. So let's kick it off with first just looking at atomic masses. Atomic masses are decimals because they are the weighted average of naturally occurring isotopes. So if you're writing with a pencil right now, there's graphite in that pencil. That's one of the allotropes of carbon. And carbon is made up of a variety of isotopes, most commonly carbon-12, very small amounts of carbon-13, and even smaller amounts of carbon-14. So we can't say every carbon atom is the same, because they're just not. That's not true for most of the elements on the periodic table. But we need to talk about a way of weighing them and what mass they would have. So we get a weighted average atomic mass, and that's why if you look at a periodic table, I'll just go to one right now. There's a periodic table, and if you find carbon in the upper right, it says its atomic mass is 12.01. It's not exactly 12 because it's a weighted average of mostly 12 and very small amounts of things that are more than 12. So let's mathematically show how we get those atomic masses from these averages, and even how we can turn it around. Starting with this example of copper. So copper is primarily two isotopes, copper-63 and copper-65. And sometimes we have mass spectrometers that can actually give us masses of isotopes to even more precision than whole numbers. So I'm going to use these, 62.93 and 64.93 atomic mass units. And mass spectrometry, as we remember from our first unit, tells us how much of each isotope there is. So the atomic mass is the percentage of each isotope, so 69.09% of that 62.93 isotope, plus the other percentage, 30.91%, so I divide by 100, of the other isotope, 64.93. And this is how we get a weighted average. And if I plug that into my calculator, I've already done that, I get 63.55 atomic mass units, AMU. And we can do a little self-check just to ask ourselves, does this number make sense? Well, yeah, first of all, it's in between 65 and 63, and if it's some kind of average, it must be. But it's closer to the 63 number, and that makes sense. There's more of it. There's more than twice the amount of the 63 copper isotope compared to the 65, so it's much closer to the 63. We can turn this around, and we can actually use the weighted average and the mass of the individual isotopes to figure out the percentage of each. So here's an example where we would do this for lithium. Lithium's atomic mass as a weighted average is given as 6.941. And if I want the average, if I want the percent of each, I'm going to define X as my percentage of the lighter isotope, 6.0151. And then plus, what's my percentage of the other isotope? Well, there's only two of them given, so they would have to add up to 100. So the other one would be 100 minus X percent times the mass of that other isotope, 7.0160. Got to do some algebra here. I'm going to multiply through everything by 100. That turns my left-hand side into 694.1 is equal to, and I'm going to start to distribute these x's, 6.0151x, plus I'll distribute this as well. That gives me 701.60 minus 7.0160 times x, and I'll rearrange things and solve for x, and I'll let you check that you can get this, but you end up getting x is equal to about 7.5%. And remember, we defined that as our percentage of the lighter isotope of lithium-6. So to get the percentage of the other isotope, I just subtract from 100, so it's 92.5% of lithium-7. And we could certainly get those percentages from a mass spectrometer, but maybe we only got the final atomic mass and we know the masses of each isotope. This was a way of getting those individual percentages. So that's how we convert atomic masses into percentages and percentages into atomic masses. Now the main reason we do this is we get what are called molar masses. A mole is the exact number of atoms found by definition in 12 grams of carbon-12. And every chemist should know Avogadro's number. There are 6 times 10 to the 23rd anythings in a mole of a substance. That is a quantity we'll use quite a bit. You probably saw that in your intro chemistry class, so I'm just reminding you here. A mole of a substance, if we scale it up, has a mass in grams equal to its atomic mass. What do I mean by that? Well, lithium weighs 6.941 atomic mass units, but that means 1 mole of lithium would be 6.941 grams, because we're scaling it up based on the definition of the mole. And that's true for all the elements you see on the periodic table. So let's practice this and get some molar masses of these compounds. To get that, you just add all the atomic masses for each one. This is the compound sucrose. There are 12 carbons. And I'm actually going to round some of my atomic masses for the isotopes that are primarily just one. For the elements that are primarily just one isotope. In fact, I'll give you what I consider my rule of thumb of when it's okay to do this. It's just to make the arithmetic a little bit easier when your main goal is to not get the molar mass, but to use the molar mass for something else. So this chart over here is just what I would consider to be a chemist's commonly rounded atomic masses. You are so okay to never round your atomic masses. You'll get a more precise number that way. But the precision that's given is based on what periodic table you're using, so there's a little bit of wiggle room with that. Carbon is primarily 12, so I'm going to round it to 12. There's 22 hydrogens, mostly weighing 1. There's 11 oxygens, and they're really close to 16. You add that up, you get 342, and the units become a gram per mole, because that's the mass of sucrose present in 1 mole of sucrose. I'll label this so you can too, to remind yourself that that's the formula. Actually, that's the molecular formula of sucrose, but it's also the formula of many other things. They are what are called isotopes. So just hit pause for a second and go ahead and prove to yourself that you can do that for these other 2 compounds. What's the molar mass of calcium carbonate and copper 2 sulfate pentahydrate? Okay, let's see how you did. So calcium carbonate, calcium is 40, carbon is 12, and oxygen is 16 times 3. You add that up, you get a very nice even 100. The SAT chemistry test loves to use calcium carbonate because it's a very easy molar mass to do conversions without a calculator. Now, copper sulfate. Copper is not on my list of roundable elements. Its atomic mass is, as we saw up above, between 63 and 64, so I'm going to use 63.55 for the copper. Sulfur I'm going to round to 32. The oxygen is 16 each. But then there's 5 of these water molecules, so that's 10 hydrogens and 5 more oxygens, or 5 times the mass of a water, which is 18, 2 plus 16. So I'm going to say plus 5 times 18 for the waters. This is called a hydrate. And a hydrate is a special type of compound that actually has water molecules embedded in the solid state. This is still a solid, but there's a crystal lattice that has a certain number of water molecules for every copper sulfate ion pair. It's just how they work. And we add them to the molar mass. You get 249.55 grams per mole, pretty close to 250. another one you might see on the SAT, because it's a pretty easy number to round to 250 and do calculations. All right, that's just reference information. Now, what do we do with these? We do conversions. We can talk about molecules and atoms and elements in terms of their fundamental quantities, and using the mole just scales everything up. When we say a mole of something, it's kind of like how bakers say the word dozen. It just means a number. But the mole is a very, very big number because atoms are small. So we're not counting atoms, we're weighing out grams, and relative masses of elements and compounds tells us how many of them there are based on the mass of those things. So the rest of this is just to show you how to do some conversions from one unit into another. And this is going to use what's called dimensional analysis, which we'll use a lot in this course. And that's just taking one unit in some value and converting it to another one. And we're going to start real slow. We're asked how many grams. So I'm going to write question mark and the unit asked for grams, and then equals, and then my given value, 6 atoms of AM. That's the element americium, a big heavy element down in the bottom of the periodic table. And then to do a conversion, I write a blank empty fraction, and I need to fill in quantities that are equal to each other. That gets me out of one unit and into another. And if I don't know where to go, I start with the unit I'm currently in, and I simply write that in my denominator. So I'm going to put atoms of americium in the denominator and ask myself, what do I know about some number of atoms of americium? Well, this is where Avogadro's number comes in quite handy. There is 1 mole of americium per Avogadro's number, 6 times 10 to the 23rd atoms of americium, because there's 1 mole of anything in Avogadro's number of whatever that anything is. We're not there yet. We want grams, and we are in moles. So let's write another fraction. And I'm currently in moles of americium now. I can actually cancel my units along the way. Atoms of AM, we are in moles of AM. So I'm going to write moles of AM in the denominator and ask myself, what do I know about a mole of americium? Well, the periodic table tells me that 1 mole of americium is 243 grams of americium. So we've done it. We've converted our atoms, which is very small, only 6 of them, into the mole. Slide this over and just do the calculation. And when you plug those numbers in, you get 2 times 10 to the negative 21 grams. I rounded to 1 sig fig because it was given as 1 sig fig, I guess with the 6. So a very small number, and that makes sense. We're talking about just over a handful of atoms, literally. That's going to have an immeasurable mass. So I'd like you to hit pause one last time and see if you can figure out the remaining 2. How many atoms are in a mass of aluminum? That's really turning this around. And then, similarly, how many atoms are in this many milligrams of a silicon chip? Try that now. Okay, number 5, how many atoms given 10 grams of aluminum? So the first thing I do is write a fraction. I put my mass of aluminum. If I don't know where to go, I'll try to go to the mole. In 1 mole of aluminum, there are 27 grams of aluminum. That's based on the periodic table when you round to the nearest whole number, which aluminum is pretty close. And then another fraction, I'm in the mole, so I'm going to get out of the mole. And then get into atoms. There are 6 times 10 to the 23rd atoms per mole, and we're there. So 10 times Avogadro's divided by 27, I get 2.23 times 10 to the 23 atoms of aluminum. So this shows us how we can take those conversion factors, the molar mass, and write them however we need to convert from one unit to the other, because if I have it in grams per mole or moles per gram, they both are valid, and I just use whichever one works based on what I'm starting with right beforehand. Same with Avogadro's number. There it is in one direction, and there it is reciprocated. Okay, last one. How many atoms? Again, given a mass of silicon, this is 5.68 milligrams. So first I need to get out of milli and into just regular grams. Well, there's 1 gram per 1,000 milligrams. And then if you look up silicon, there's 1 mole of silicon per 28.09 grams. And then we want to get into Avogadro's number of atoms. And then a mole. And that gives me 1.22 times 10 to the, I think you get 20 atoms. And you could do a little self-check, a little tiny silicon chip. Yeah, that's still going to have a lot of atoms, but way less than a mole. Okay, so that's how we convert units of an element or a compound into other units of the same substance. It's using atomic masses and molar masses, which are essentially the same thing, just one refers to an element and one refers to a compound. And those atomic masses are weighted average decimals for the most part because of different isotopes.